Okay, so our first example here is actually one we can work out by hand, but we're actually going to approach it. Well, we're going to do it first by hand, and then we're going to see how we can actually use an integration table to help us with this problem. So, but I want to do it by hand because it reviews a technique of integration that we have available to us. And that's the idea of recognizing with that 1 plus sine, 1 plus cosine stuff, how we can bring in, that's the right word here, the multiplication technique of multiplying by 1. So here we have a 1 plus sine. So what we do is we recognize that with a 1 plus sign in the denominator. If it was just a 1 plus sign in the numerator, it wouldn't be an issue. We'd just integrate each piece. But here we would multiply by 1. We multiply to make that denominator become a difference of squares. The idea being that that will let us transform over to an integral, or at least the denominator being something involving cosine. So doing so gives us 1 minus sine x over 1 minus sine squared x dx. And of course, 1 minus sine squared is simply cosine squared. And that now allows us to break this integral up. So I can break it up as the integral of 1 over cosine squared, which would simply just be the integral of secant squared dx, minus the integral of sine x over cosine squared x dx. And of course, my natural instinct when I see that cosine squared in the bottom is to think substitution. And in fact, that's actually what I do here. Because I recognize that I have cosine there and I have what I need for the derivative of cosine right up there on the top, the sine x. So du here would call for a minus sine x dx. And it turns out I have all of that stuff right there. The minus sign and the sine and the dx. So everything's perfect to just carry through the substitution, which would transform our integral into an integral of 1 over u squared, or u to the minus 2 du, which would make that u to the minus 1 plus a constant. So that one we're now ready to carry through, because u to the minus 1 would just be 1 over u, or in this case 1 over cosine. So now we can go back and work out the whole integral. The integral of secant squared is one that we recognize, that's just tangent. And this will actually be minus 1, right? Because add 1 to it, you get minus 1, and we have to divide by it. So minus 1 u to the minus 1. So that will be minus 1 over cosine x plus a constant, or better known as tangent x minus secant x plus a constant. Okay, so we've worked out the integral in terms of x. We've got the integral now in terms of x. Okay. And so there we have our answer, tangent x minus secant x plus a constant. However, I also want to look at this using a table of integrals. So we can introduce this idea of using integration tables. So I mentioned again how to get to this. You can go from your eText, click the very first link, view the eText that mirrors your textbook. Get to this then by going into the table of contents, and at the very bottom of the table of contents is your table of integrals. And that's where we're at right now. So there's, I believe, a little over 100 different integral formulas that your textbook has, from the basic ones onward to more complicated ones. You can see here, there's our inverse tangent formula, one for an inverse tangent one, inverse sine, inverse secant. There's a formula for how to do the integral of inverse cosine or integral of inverse tangent or inverse sine. You can see your hyperbolic integrals that we mentioned briefly. There they are. Some of your trig integrals for specific powers of trig functions. Keep going until finally I reach number 44 here. Okay, on my list. Number 44 is the integral of dx over 1 plus sine ax. Notice that is the same. Our integral doesn't line up exactly. Ours was dx over 1 plus sine x. It didn't have a number in front. But this matches that formula. This matches that formula. Okay, so this matches that formula. And so that's what we're going to actually use here. So formula number 44, just copying it right there from the table. We're taking formula number 44, integral of dx over 1 plus sine ax, and that tells us it's equal to minus 1 over a times the tangent of pi over 4 minus ax over 2 plus c. So I'm just taking that formula there, number 44, as it is, and I'm just going to put that down here. Right. Integral of dx over 1 plus sine ax is negative 1 over a tangent of pi over 4 minus ax over 2. Okay? So we're going to use that formula. Now that's something that looks different than what I have here. Right? That looks different than what I have here. Absolutely no question about it. That looks quite different than what I have here. But that's okay. These two things are actually equivalent. We'll see that in a moment. You could get it with trig identities if you went back and used your tangent identity and maybe did some manipulation with that. You could probably get to that result. Okay. So let's take a look at how to do that now. So our integral, our original integral of dx over 1 plus sine x fits that format where a in our problem is equal to 1. So ours would be minus 1 over a, so minus 1 tangent of pi over 4 minus ax over 2 plus a constant. Okay, that would be our function. And so really quick, and that's the nice thing, really quick here. To do that took almost no time at all compared to the doing it by hand. The last thing I want you to recognize that this is in fact the same. So I actually graphed these two functions on Desmos. So there's my first function, tangent of x minus secant of x. And there's my second function, negative tangent of pi over 4 minus x over 2. So first, there's the red graph, you can see. And then there's the blue graph. Well, I don't have the red highlighting. You can see they lay right on top of each other. Okay, so the two graphs do line up graphically. Now, we could go through algebraically using a tangent identity for a tangent of a difference of two angles and get somewhere from that, right? Make some progress with that, and maybe do some other identities and eventually be able to manipulate it to show that that's the case. Okay. Take a little bit of work, but we could probably get there and do that. It would just be a little bit of work to get to that point. Okay. So we're not going to mess with that. Just that we can see graphically they agree. And so that's often the case with integrals worked out with one method compared to another, especially with trig functions, that they're often a little bit different.